Are you late? I just went live. You're not late. 1:40. Getting the right time again. Okay. What's up, Garlene? What's up, Salim? Okay. Unit testing. It's gonna be fun. Think I got everything. What's up, Dermy? Color in my teeth. Not a good start. Hey, so I was listening back to the previous lecture, and the audio was kind of jacked up. Can someone confirm or deny if the audio is any better? I tried playing with it a bit. Only 12 people in here right now. Yeah, but I just went live too. There'd have to be people sitting there waiting on the page and refresh to see that I went live. I gotta start going live a little earlier. Audio is better. Good. Seems better. Yes. Good. I listen back. I don't rewatch every lecture, but I watch a few seconds of it just to make sure things went well. And yeah, the audio was so jacked up. If that happens again, y'all don't hesitate to let me know. Start blowing up chat and being like, dude, your audio sucks. I have a nice mic and everything. There's no reason for the audio to be that bad. All right, 11 o'clock. Let's go. All right, so today, so first of all, brief announcements. I don't have much for announcements, but all 8 programming tasks are available. The programming tasks, oh, I have to refresh. If they don't show up, hit refresh. They're there. All the way up to 8. The programming tasks are listed on the lecture where the material is covered for that lecture. So like programming task 8 is all about graphs. So it's in the graphs lecture, and then it's due 1 week after June 29th. It's due 1 week after July 6th for the expected deadline. Ooh, that should not say June 13th. That should say July 6th. Oops. I'll have to fix that. And then the actual deadline for all programming tasks, of course, is the day after the last day of classes. So today is the first material that's going to be covered in a programming task. Programming task 1 is pretty much the intro to Java and unit testing, intro to unit testing homework. Really just intro to the course in general. Here's what Java is, here's what unit testing is. And is that true? Yes, every programming task will have a testing component. So unit testing is going to be a big deal throughout the entire semester. And it's generally speaking, students will spend more time writing their unit tests than actually writing their code, the code itself. Which is actually true, carries true for industry as well. When you get out there and start writing code, it takes longer to make sure that your code is right than it does to actually write the code itself. And sometimes when you're testing to see if it's right, of course, sometimes it's actually wrong. You expose the bugs, and then you go fix the bugs. So we want to talk about all that. We do have 50 minutes of Java left, Java intro. We got to talk about some data structures. So let's get into it. And the important takeaway of this intro is that after today's lecture, you have everything you need to do programming task 1. And again, it's a 6-week lecture. I'm going to try to not mention this so, every lecture throughout the entire semester. But it's only a 6-week semester. Getting started on programming task 1 right away is going to be important. I didn't update my office hours. Let's see if Garlene added any more. But I will do office hours right after lecture today. Can I just do that right now? And my intention is to keep that office hour schedule through the semester, and then depending on how things go, I might add more office hours. But we'll see how things go. I was pretty lonely on Tuesday's office hour. Of course, no homeworks were out yet, so you know, there wasn't much to talk about. But if office hours start getting busy, I'll add some more. But let's get into it. Save. I have to open the folder. That's just the way I'm going to have to do it, huh? Presentation. All right. No one was there yesterday either. Oh, that's sad. I had 2 students just with really quick questions. No one had any coding questions yet. Yeah, when's deadline time? And the deadlines are going to come quick. Next week is the first expected deadline for this programming task 1. So next Wednesday, Gerline, you're not going to be lonely. There will be lots of visitors. All right, Arraylist and Hashmap. Let's do it. Before we get into our data structures, we've already had 3 memory diagrams, so I want to talk a little bit about what memory is even. When I say memory, like what even is that? So when I say memory, in this, at least in the context of this course, I mean RAM, random access memory. Not to be confused with the hard drive. Hard drive is a whole separate thing that we call usually disk space in programming terms. In programming, whenever we say memory, we mean random access memory. These RAM sticks. If you ever built your own machine or you've cracked open your laptop, pulled the screws out and everything, you've seen these things. Usually green, but if you get high-end gaming RAM and stuff, they come in all kinds of fancy colors and shit. But this is where everything is when we talk about memory in this course. And what this is effectively one giant array. You have one giant array, and there are what we call memory addresses, which are the indices of that array. So you can ask memory, hey, give me the value at this memory address, and it'll give you the byte at that memory address. So this is where everything is stored for your program, at least until we start, at least until we start talking about file I/O. File I/O files are stored on disk. Everything else, everything in your memory diagram is on RAM. So when you start your program, what you do is you talk to your operating system and you say, hey, operating system, I need some memory. I'm going to run this process. I'm going to run my program. I got this beautiful Java program that I want to run. And what it's going to do is give you a slice of that RAM. It's going to say, okay, here's your space where you're allowed to work. You can do whatever you want with this memory. And I'm going to keep every other process on this device away from that section of memory. And this is what we call your stack space. Stack memory has a bunch of different names, but as long as the term stack is in there, that's your slice of memory. That's your home to work with, where you can store all your variables, your stack frames, all your stuff goes here, all your code blocks. That's where all your stuff is going to go. And you can't go over the bounds of that space. If you use up more memory than what you were given when you started your program's going to crash. You're going to get what's called a stack overflow error, which you probably heard of from our favorite website. Stack overflow means you ran out of stack space. You tried to use this next memory address that's used by another program, or it might not even be used, but the operating system did not say you're allowed to access that memory. It's still in the operating system's control, so your program crashes. And just a little bit of a nuanced point. It might be on my next slide, actually. No, it's not. A little bit of a nuanced point. I'll say operating system usually when I'm talking about memory management. Since we're working with Java, which runs on the JVM, usually Java, like our programs, are going directly to the JVM. The JVM has a big chunk of memory that it got from the operating system, and then the JVM is going to parcel that memory out to our specific Java programs that are running. So I'll say OS kind of as a shortcut. The concept of memory, your memory is managed by the operating system fundamentally. So when you're talking about a language other than Java, this is more accurate. I'm kind of language independent right now in this slide. But since we're Java, we'll have that intermediary, the JVM. But memory management is out of our control. When you take CSE116, memory management will be in your control for the most part. You still have to talk to the operating system, but you'll talk to the operating system directly, which has lots of unique challenges. So whenever we store our variables in memory, they're going to go on the stack. Yeah, I'll just leave it at that for now. When we talk about objects, that's going to be a little different. But for now, every time we create a variable, it's going to go on the stack, and then that variable is going to have a value. Whenever we call a function, we're going to create a stack frame, and that stack frame is going to be its own isolated section of stack memory. And when you're inside a stack frame, you can only access variables that were created inside that stack frame, and you can't access any variables that were created outside of that stack frame. So stack frames are effectively their own little mini portion of the stack that acts as its own very own stack. And the stack, we call it a stack because it does follow the stack data structure of last in, first out. So we can only ever access variables, or rather stack frames. The stack is really a stack of stack frames. We can only access variables in the stack frame that's on the top of the stack, which we draw the stack upside down in our diagram, so it gets a little backwards. But the stack frame that's on the bottom of our stack visually, but the top conceptually, that's the only stack frame that can be accessed. It's the only stack frame that can be removed from the stack, and we can only add stack frames on top of that last stack frame. So it's a last in, last out, last in, first out data structure. Think of it as like a stack of papers. You can only add a paper to the top of the stack or remove from the top of the stack. And that top of the stack is the active stack frame. That's the only one that's currently executing. The rest of the stack might as well not even exist while that stack frame is running. And same with variables. Variables within a stack frame are added in the next available memory location. So the reason we're talking about memory in a little bit more detail right here is because we're going to introduce heap memory today. Arraylists and Hashmaps are stored in heap space, or heap memory, and this is a different type of memory that's more dynamic than the stack. So the stack, you just get your portion of the stack when you start your program, and that's fixed. You can't change that. You can't, while the program is running, say, hey, operating system, I need more stack space. Doesn't work like that, can't work like that. Your stack space is your stack space, period. If you need any more memory, if you want to store large amounts of data, especially, or data that's going to be changing, data that's more dynamic, we're going to ask the operating system, or JVM in our case with Java, we're going to ask the operating system for more memory as the program's running, and it's going to give us memory in heap space. So it's going to give us some heap memory, and it's going to give us however much memory we ask for. If we ask for too much, the program will crash, but those limits we're not going to get near in 116. But we're going to ask for some extra space whenever we need it, and the operating system's usually going to comply unless something's going wrong. It's going to say, here's your space, and that space can be anywhere in RAM. It doesn't have to be co-located with the stack space. It could be on another RAM stick entirely. It's just somewhere in RAM. Somewhere there. You get another chunk of RAM for the amount that you asked for the data that you asked for. So if I want an array list with 100 elements, I'm going to ask the operating system for enough space for an array list with 100 elements. Then the operating system is going to comply. Give me that RAM. And then it's only going to give me a reference to that memory location where it allocated space. It's going to give me a reference of where I can find that memory. So it's going to allocate the memory, which means it takes a chunk of RAM somewhere that's the appropriate size that we asked for. It's going to allocate that for us, which means it's going to tell every other program on the device to back off that space. That's for us, for our program. And then it's going to give us the memory reference, which is effectively a memory address saying, here's where you can find the memory that I am controlling for you, that I'm not letting anybody else touch. Here's where you can find your memory. And then we can store whatever we want in that memory. And then using that reference, we're going to store that reference in our variables. so our variables know where to go on the heap. That reference is like a roadmap. It's going to be your instructions on where to find that value on the heap. All right, so with all that in mind, let's talk about what an array list is and how the array list is going to leverage the heap. All right, so here's some code. I'm going to throw a bunch of code at you. I'll do this a lot throughout the semester, by the way. I'm going to throw a lot of code at you, and then we're going to explain it over the course of like 15 to 20 slides. So don't worry about understanding all of this code right away. I'm going to talk about it for quite a while. So an array list, it's like your list in Python, your array in JavaScript. If you did 115 here, be like your vector in C++. If you're coming from C++, I don't know what other language. There's a language that someone's familiar with that isn't one of those three. Those are usually the big ones, or Java itself. You can let me know. I'll give more parallels. But it's a sequential data structure. Order matters. You have indices. Values are stored at indices. No matter what language you're coming from, you've dealt with some data structure like this, or just like a plain array in C. It's a little different than that, but let's not get lost in the details. Okay, so array list is the first type that we're using that isn't automatically imported. So there's certain things in Java that are just automatically available in any Java program ever. These are all of our primitive types, our strings, arrays. I guess we didn't use those really. System is automatically imported. So just every Java program. They're so ubiquitous. So many people use them in so many programs that Java just says, you know what, we're auto-importing those. You don't have to tell us that you want to use system or string. Array list, not so much. It is still built into Java. It comes with the Java language, but you do have to explicitly import it to be able to use it. So we're going to add our import statement, and the import statement must contain the fully qualified name of it's actually the class. Oh, we've talked about classes. The fully qualified class name for the class that you want to import, that you want to use. So we're going to import a class that lives in the java.util package. So util is a sub package of the Java package. So we have a package util that's defined inside Java. If you've cloned the homework code, you have a ratings package and then a data structures package within that package. So anything in that data structures package would be ratings dot data structures dot whatever class you want to import. So in the java.util package, there's a class named Arraylist, a file named arraylist.java, which matches the class name, and that's what we want to import. We want to be able to use that Arraylist class in our code. So we import it. This is the only other thing besides the package declaration that goes outside of your class defining the file. Everything else is inside the class, and this would be in a file named arraylist1.java. Because it's your first ArrayList example. Okay. And then when we want to create a new array list, this is unlike string and all of our primitives. Again, another case where strings do act like primitives. That's why we put our strings on the stack and our memory diagrams, even though it's technically incorrect. But they behave very much like primitives. ArrayList is our first thing that acts like a class. And we're going to create an object of type ArrayList. We're going to get into a lot more detail on what that means in the next lecture when we start creating our own classes that we're going to create objects of. For now, if you want to create a new ArrayList value, I'll say that value will be, getting a little ahead of my slides here, but a reference to an object. We're going to use the keyword new. So we're going to say new ArrayList, and that's going to create a new ArrayList on the heap, and it's going to return a reference to that ArrayList that was created for us on the heap. When we create a new ArrayList, we have to have these angle brackets. These have to exist. This is like a second parameter list. It's the type parameter list, or the generic type parameter list, and then the actual parameter list. We are calling a method here, so we must have our argument list, even if that argument list is empty. So we have an empty type parameter list and an empty argument list, but both of those things have to be there or else Java gets mad. Java's not going to like it so much. And then the type of our variable, this is where we do have to specify the type parameter. So we're creating a variable of type Arraylist, and at first you might just think, well, we're going to have a variable of type Arraylist. We're going to say Arraylist array1. But we have to have one extra thing in there. In Java, because Java is strongly typed, and its data structures are also strongly typed. This is a huge restriction that we didn't have in Python or JavaScript. There are important reasons and very valuable reasons why this is the case. But a data structure in Java can only store one type. So we don't just create an array list. We create an array list of integers. We create an array list of doubles. We create an array list of strings. Or we create an array list of array lists of integers. But we have to have some type here. It can be any valid type, including array list of integer itself, like as I just mentioned. But it has to be a valid type that's defined by a class. And then this array can only ever store values of that type. So not only do our variables have to have types, like we talked about in the last lecture, every variable has to have a type and it can only store values of that type, but every data structure has to have a type parameter and the data structure can only ever store values of that type. So we have a few restrictions that we didn't have when we had loosely typed languages. And these type parameters, I said they have to be types that are defined by classes. That means we can't use our primitive types. Anything that starts with a lowercase letter is a primitive type. Can't store those in data structures. They cannot be a type parameter because they are not a class type. So we cannot have array list of lowercase int. Can't have it. Java will throw errors, Java will get mad, and will refuse to run your code. So luckily, we do have an answer to this. Java said, yeah, that's pretty bad if we can't have an array list of integers. So Java has what we call boxed classes. Is that the right word? That sounds wrong. But auto boxing is definitely a thing, but boxed classes? I don't know. I forget. But these are the equivalents to our primitive types, but with full class definitions. So integer is the class. It's a class called integer with all the integer methods and integer things that you would expect, but it is an actual class, not a primitive type, where a primitive type is really baked into Java, and it just stores the value of an int, has no methods, nothing else. It's just a value. So if we want an array list of integers, we use capital I integer. If we want an array list of doubles, we use capital D double. If we want an array list of booleans, capital B boolean. And then there are equivalents for all the other primitives, but we didn't even talk about any other primitives. I guess char, character, capital C character instead of char is the equivalent to char. Yeah, if you want that array list, you would have to have an array list of double. Since you have some values that have decimal portions, you would have to have an array list of double, and then the 0 would be 0.0. It would be auto-converted by Java. The 0 would be auto-converted to a double when you created that array list. It would be your 0 would be converted to 0.0 as a double. So we can use these class types, these class equivalents of our primitives. And Java is usually good about converting between them with something called autoboxing. If you have a method that takes a capital I integer, for example, and you give it a lowercase I int, Java's going to go, oh yeah, I'll just convert that to an integer for you. Like, no big deal. I got you. So in most cases, Java is really good about this. There are cases where it's not. And one very important case where it's not is when you're submitting your code to Autolab. When you're submitting your code to Autolab, do not use capital I integer, capital D double, capital B boolean if the homework assignment says write a method that returns an int. So in general, in my homework descriptions and in my personal programming and everything, if I'm coding in Java, I'm always going to use the primitive type unless I have to use the class type. So in the homework assignments, it's always takes an int, returns an int, takes a lowercase d double, returns a lowercase d double. It's always going to be those types unless it's part of a data structure. If it's the type parameter of a data structure, it's the only time where it's going to be capital I integer, capital D double, capital B Boolean, etc. I spent a while on this warning last semester. I'm spending a while on it here right now too. And last semester it was a shit show in office hours when the first homework assignment where I said return an int, which is programming task 1, and so many students are just using capital I integer, and I don't even know why. I asked them, I'd confront them, and they'd be like, I don't know why I use that. I suspect that's because they didn't write their own code. I think that's one way to catch people doing nefarious things. But if you're writing your own code, for the love of God, just use int. If the homework says write a method that returns an int, write a method that returns an int. Some students wasted hours of their life because they had capital I integer instead of lowercase I int. So don't be one of those people. All right, now let's get on with that. Spent too long on that. So when we want to work with the values of an array list, we have two primary methods that we'll use, add and get. We cannot use our index notation like we would in other languages, where we just use these square brackets and access and modify the values that way. Instead, we're going to use the methods get and add. Add is going to insert whatever we give it, which has to match the type of the data structure of the array list, has to match the type, and it will add that in the next available index. And then get is going to take an index and then return the value at that's stored at that index. So we have to use get and add instead of our convenient notation like this. Let's see how this works through a memory diagram. It's been almost 48 hours since our last memory diagram. Let's do another one. So do we just use the class integer double etc. for defining array lists and int double etc. for the rest? Yes. Array list and hash map. And we'll see a few other cases throughout the semester where we'll, like for example, when we talk about linked lists, we're going to create our own data structure, a linked list data structure. We'll use type parameters there. But outside of type parameters for data structures, we're going to use the primitive types. All right, so memory diagram. This should be getting pretty familiar except for the very first line. But the setup, we have our stack, we have our heap that we're actually going to use this time, and we have our input output. And we're going to start with the main method. When we run this code, everything always starts with the main method. So we start with main, and then very quickly get into something very, very different. It's going to take us a long time to get through just this first line. So buckle in. It's going to be fun. So we create a variable named R1. We don't put our types of our variables on the memory diagram. So we already know how to do this part, at least the left-hand side of this equal sign. We're going to put a variable named R1 for array 1 on the stack. But what's the value and what's all this going to do is the tricky part. So array list goes on the heap. We cannot store an array list on the stack. We can't just put our array list as the value of our variable of type array list. It's not how it works, and it can't work like that. See if I can come up with a brief explanation of why. It's because your array list is going to be changing size. And if you put another variable right after this, since the stack is sequential, this is one continuous block of memory. Once you put another variable right here with a value, that is actually right next to that value in memory, at least in the next memory address. And then you want to add an element to your array list, you can't because there's no room for it. You can't expand into the next variable. So that's my brief explanation of why it's got to go on the heap. Got to go on the heap when you have more dynamic data, like a data structure. So it's going to go on the heap. So when it goes on the heap, we're going to create this kind of a T-chart, which is going to be very similar to our stack. How we have this T-chart of name and value. It's going to be this similar, same-ish thing, except the names are going to be the indices, and then the values are still going to be the values. It's the values stored at that indice. So we have two columns for indices and values stored at those indices is how we're going to represent this in our heap space. And then we're going to give this array a memory address. Our very first memory address, you're going to see lots of these throughout the semester. Our memory address is going to be some value, some made up value. We're thinking of changing how we do memory addresses because this does confuse students. The question is always, where did 0x200 come from? So 0x means that this is a hex value, and the 200, I just made it up. When I was making this slide, I picked a number. I like to stick with 3-digit numbers for these. I don't know why. I just do. Probably because that's what Paul does, and that's what, when you run the debugger in IntelliJ, they're usually 3-digit numbers too. So I just stuck with that. So I just picked whatever 3-digit number I'm feeling when I make the slide. 200 is completely made up. You can make up whatever values you want for your memory addresses in your quizzes, in your memory diagrams, but it has to be some value for the memory address for that object on the heap. So we made up a number. And this is going to be the location of that object on the heap. Now the number's made up. Of course, it's going to be an actual number when you run the program. The JVM, the operating system, they're going to negotiate. They're going to figure out where in RAM to put this. And that value is representing where in RAM it ended up. Now, we don't know where it's actually going to end up when a program is ran. So in our memory diagrams, we're just going to make up values and say, well, this got memory address 200. And that's where that object ended up. And then what new returns, when we say new and create a new object, what this resolves to, what this expression resolves to, is the memory address. This value, what this resolves to, is not an array list. What this did is created an array list on the heap at some location, wherever we got access to some memory. When we asked for memory, we got some location, we set up our array list there, and then this returned only that 0x200. That's what new resolves to. It resolves to a memory address only, just a memory address. And then that's what we assign to the variable R1. So R1 does not store an array list of integers, even though that's its type. That's what we would want to think that it stores. And throughout the course, I'll probably say array list stores, R1 stores an array list of integers or something, because I get sick of saying it the right way, excuse me. But R1 actually only stores a reference to a memory, to an array list in memory. So R1 only stores the memory address, 0x200 in this case. And when I say the number doesn't matter, the 200 is just whatever I was feeling when I made the slide. It's unimportant what that value is, but it's extremely important that these values match. I have to stay consistent. Once I say this is 0x200, wherever I have a reference to that array list in my memory diagram, I have to make sure I'm consistent and put that 0x200, because that's how we know that R1, because it has the value 0x200, I know it refers to this array list at index 0x200. So I have to stay consistent, but I can choose any numbers that I want. I've seen students do 0x1,0x2, 0x3 in their memory diagrams. That's perfectly fine, as long as everywhere where you have a reference to that 0x1, it actually is 0x1, then 0x2, 0x3, wherever need be. So array list has the roadmap only. Doesn't store an array list, it stores the roadmap, the instructions, the directions. How do I get to that array list? Go straight, turn left at the intersection, go 5 miles down the road, turn right, and then it's the first memory address on your left. that's the only thing that R1 stores. And then whenever R1 needs to access that array list, it's going to read those directions, head over to that location in the heap, and then do whatever we asked it to do to that array list. R1 does not store an array list, it stores a reference to an array list. All right, any questions on array lists? Oh, there it is. I turned down the latency too. We got a lot less lag now, looks like. So I don't have to wait forever. I can ask for questions and then not have to wait 15 seconds. Are we going to have to highlight the memory address on our memory diagrams? That's just for the slide. So there are things that I do just for the slides that I can only get away with because it's the slides. And that's one of them. I'm going to color code my memory addresses just so the slides are easier to read, easier to understand when you're learning this stuff for the first time. You can just write the memory addresses. But if you do want to bring like a whole box of colored pencils to your to the quiz, or bring, I guess you're doing the quiz at home, but you're welcome to do that. I ain't going to stop you for sure. It'll make grading a lot easier. What happens to the heap memory once the stack frame is deleted? So that's the fun part, is it stays there. So when a stack frame is deleted, and we'll get into this more in the next lecture, but when the stack frame is deleted and there's a variable that had a reference to an object on the heap, that object on the heap remains, and we can actually have methods that go over to the heap, make a change to an object on the heap, and then that method might even return void, but we can call it for its side effect of heading over to the heap and making a change. So we can give a method in directions to find an object on the heap as a reference. That stack frame can head over to the heap, make some changes, return void, but then we can actually see the changes that it made, even though it didn't return anything. So that's when side effects, we saw the side effect of printing to the screen. We're going to see side effects of heading over to the heap and making changes to objects that persist beyond the lifetime of that stack frame. So that's going to be a huge topic. We're not going to get into that today, right? No. Yeah. But next lecture, when we talk about classes and objects, it's going to be a big topic. Like 4 or 5 seconds. Ain't too bad. Hey, there's an ultra low latency option too. I don't know what the downside of choosing that option is. Maybe I'll try that one next time. Go even lower latency. All right, and then let's do a loop. I'm going to skip a lot of the details of the loop. I'll talk through it, but I'm not going to show too many details on the slide. I guess we only saw 2 loops. Maybe I should spend a bit of time on this. But let's see a loop. So our for loop, as we saw last time, the initialization statement is executed inside the code block for the loop. So X is declared inside the code block. We draw a dashed box because we can access variables that are outside of the code block from within side. So I like to call it semi-permeable. We can cross this line and access R1, which we're about to do here. We access R1, even though it's outside of this code block, we can still access it because we can jump outside of a code block. But once the code block ends, X is gone, R1 is going to remain, but X will be destroyed. And then we're going to call R1 dot add. So the dot, come on, who made these slides? It was me who made the slides, but who made these slides? Why does this not explain the dot operator right here? This is important. So R1 dot. So R1 is just a memory address. We almost never want to deal with R1 directly because we can't do anything with a memory address. There's only one thing we can do with a memory address that we care about, at least, is read the directions and head over to the heap. And we do that with the dot operator. So R1 dot, this dot operator right here means look, R1, I know you're a reference, and I don't give a damn about that reference. I don't care where, I don't necessarily care about the directions themselves. I just want you to follow those directions and take me to the object to which you refer on the heap. So R1 dot means take me to the array list to which you refer through your reference. So after the dot, everything after the dot is going to be after we follow the reference. So R1 dot, R1, look at the value, dot means follow that reference over to the heap, and then add 10 minus x. We're going to call that method on this object on the heap because we followed the reference, found our location on the heap where this array list lives, and we're going to call add, which is going to insert a value into the next available index. There's nothing in this array list before, so it'll be index 0. And 10 minus x, 10 minus x will be 10. Then add that value. So we have the value 10 stored at index 0. And we're going to loop through, increment x. X is still less than 4. We're going to loop through a whole bunch of times. X is going to be replaced by 1, 2, 3, and then once x equals 4, this will be false, so we'll break out of the loop and end the whole loop. X will be removed from the stack, and at this point we can no longer access x. It's deleted from memory, it doesn't exist anymore. And we called R1 dot add on 9, 8, and 7. So those values got added at the next available index. So we have an array list where index 0 stores the value 10, index 1 stores the value 9, index 2 stores the value 8, and index 3 stores the value 7 by calling add 10, add 9, add 8, add 7. And then we have two more important reference topics to talk about today. And we haven't even started talking about hash maps yet. All right, so array list of integer R2, we're going to create a variable with type array list of integer named R2. So we're going to add R2 to the stack, and it's going to equal R1. This is something that trips up students seeing this stuff for the first time quite a bit. Python actually behaved this way as well. So did JavaScript, but we kind of try to make it not come up in 1.15. We're going to make sure it comes up in 1.16 because it's one of the things we need you to understand is how references work. But this is actually the same way that Python and JavaScript worked in C++. We're going to assign R2 the value of R1, and my tip for this one is to not overthink it, especially if you're doing your memory diagram. Actually, my advice in general for memory diagrams is don't overthink anything. The computer can run your code and go through your code line by line and manage memory, put things where it needs to be in memory, and a computer has an IQ of 0. So don't overthink it. Don't let your brain get in the way and try to predict what should happen, do some pattern recognition. Just do the dumbest thing possible. Sometimes, not always, but sometimes is the best thing you can do when doing a memory diagram. So R2 equals R1. We're going to go to R1 and just look at what's sitting next to it in the value column. Don't think about anything else. You have an assignment like this and it's just a variable on the right-hand side. Go to that variable name and take a look at what's sitting right next to it in the value column. It happens to be OX200. That's what R2 gets. Whatever value is sitting next to that variable name, that's the value that you assign to the new variable. And that's it. So what we did is what's called assign by reference. So only the reference was assigned to R2. A big beginner mistake is thinking that this is going to create a new array list of integer because we created a new variable of type array list of integer. But remember, this isn't actually a variable that stores an array list of integers. It's a variable that stores a reference to an array list of integers. So array R2 is going to store a reference to an array list of integers, and we never created a new array list like we did the first time. We just copied the reference over, and array 2, R2 and R1 both have a reference to the same array list, so we say they refer to the same object on the heap. They both refer to the same array list. And doing anything to R2 is the same as doing that same thing to R1 because they refer to the same object on the heap. And technically, I got to throw the caveats out there whenever they come up. Technically, this is assigned by value, but the value is a reference. So I incorrectly usually shorten this to just assign by reference because I don't feel like every single time saying assign the reference by value or assign by value with the value being a reference. I'll call it incorrectly assign by reference just for the sake of brevity. But assign by reference is technically a different thing. I shouldn't even go here because it's been so long since I thought about it. There are memory addresses on the stack as well. Assigned by reference would be R2 getting the memory. All right. And by the way, you should be mad about that stuff. It's not assigned by reference. And when you get to 220, assigned by reference and assigning a value by reference are two very different things. It's the difference between references and pointers in C and C++. Those are two very different things. But Java only has one, so I get away with mixing them up. All right. I already talked. Did those talking? Oh, I missed the print line here. When you print an array, for what it's worth, it prints in this syntax, comma separated, and then square brackets around the whole thing. And when you print array 2, you're going to get the same exact thing because it refers to the very same array list on the heap. But notably, it's not a copy. We didn't create a new array list on the heap. They refer to the same single array list on the heap. And that's one of the big things the first quiz is going to test you on, is this understanding of references. Being the first one, it's going to quiz you on all the stack, code blocks, stack frames, and objects on the heap, printing things to the screen. It'll test all those, but the big thing, I guess what I'm trying to say is the trickiest thing is references, and it's the first true 116 topic that I need you to understand. And references will be a big thing throughout the whole semester. All right, and the last big topic pertaining to references is when we call a method that takes a variable, takes a parameter type that stores a reference. So this doesn't store an array list of integer. Our in is going to store a reference to an array list of integer. So we do pass this by reference. Yes, technically pass by value, but the value is a reference. We're going to pass the reference into the sum method. So when we call our method, we get our stack frame, we put the name of the method, we have our return arrow to where it's going to go. Total didn't exist yet, so we do put total on the stack first with no value. Its value is going to be whatever this method returns. And then R1, we're looking at the value of R1, which is OX200. That's what's going to be assigned to Rn. So Rn, our parameters, are the first things that go in our stack frames. Rn will be assigned the value of R1, which is OX200. So Rn also has a reference to this object on the heap, this array list. And we're going to create a variable inside the array list, out0. Oh, so pass by reference, it's very similar to assign by reference, that only the reference got sent to this method. Again, we didn't create a new array list. We didn't copy all the values of the array list. We didn't do anything like that. We just said, hey, sum method, here are the instructions. Here are the directions where you can find an array list of integers on the heap. And then it happily heads over to that value, to that location of the heap, and does its thing, does what it needs to do. We have another code block for our for loop. X is inside the for loop. We're going to iterate over the array list dot size. I didn't mention this one yet, but dot size, because my slide mentions it right here. Dot size is what you would expect. It's the number of elements in the data structure, so 4 in our case. And then using a loop with this setup, we're going to iterate over all of the indices. This will start at 0, and it will stop when x is less than the size, which is 4. So it'll stop when x is 4, but it won't execute the body of the loop when x equals 4. It will execute the body of the loop for x equals 0 through 3. And then each time we're going to update out using our shortcut syntax. Out equals out plus ArrayIn.getX, ArrayIn.getX. So ArrayIn dot means follow the reference. Get x, x is 0. So get the value at index 0, which is going to be 10, and then add that to out. So 0 plus 10, assign that to out, and then do that through the whole array list until x is 4. The condition is false. The stack frame is removed from memory. Make sure you cross it out. X no longer exists in memory. It's deleted. Out kept getting those values added, and we get 34 returned. When we return from the method, cross out the entire stack frame, and then the return value follows the return arrow into whatever variable we're storing it in this case total, gets 34, and then print total to the screen, total 34. We hit the end of the main method, so that's the end of the program. So if you were to add all the values from array in to out, could it work with using get, or is get only used for adding values from arrays to an int? Get will return whatever value is at that index. So if I had an array list of strings and I said get 1, then it would give me the string that's stored at index 1 in that array list. So get is used in general for any array list that you're going to have. You're going to use get a lot. All right, my time is a little off today. So let's go right into Hashmap. Hashmap, the example is a lot smaller because I don't have to talk about references the whole time. That's the big new concept today. Arraylist and Hashmap are review from Python and JavaScript or whatever language you had in your CS1. Just Java syntax, but references are the big new 116 topic today. All right, so Hashmap, this is the key value store of choice that we're going to use in 116 using Java. Quick recap, 2 bullet point recap of key value stores. Order does not matter. So where with array lists and lists, arrays, the order mattered. You had a value at a specific index and all the values were stored in order. With a hash map or any key value pair in general, the order usually doesn't matter. In some languages and certain data structures, even Java has a linked map. I always forget which one, but it has a key value store where it does preserve the order. But Hashmap will not, and in general, key value stores do not. So order doesn't matter. Order can be ambiguous, and you can't have duplicate keys. This is more so a 115 mistake that I see a lot in a CS1 course. But you can't have duplicate keys. Hopefully, you all are well aware of that at this point. If you add a value to a key value store and that key already exists, it will overwrite the value at that key. It will not store both key value pairs if the keys are the same. All right, so we have to import this just like Arraylist. And Hashmap, the first difference from Arraylist is that it takes 2 type parameters. This is a type parameter list, so if we have multiple type parameters, we have to have each of those type parameters. So just like Arraylist, the types have to be specified, but a Hashmap does allow us to have different types for the keys and the values. So we give 2 types in this type parameter list. One for the keys, so this will be a Hashmap with the keys being strings, and one for the values. In this Hashmap, the values will be integers. And the way we read this is that this is going to be a Hashmap that maps strings to integers, or just Hashmap of string to integer is the terminology I prefer in the homework write-ups. If I say create a method that takes a Hashmap of strings to integers, that means this is your type. Hashmap of string to integer is the way we would read that. So Hashmap of, I guess I should change that. From's correct too, but of is I think what I write in the homework write-ups. And then when we want to add to it, and we'll use new hash map, same syntax as the array list. We don't have to specify our types here. You actually can. You can put string, comma, integer right here. That's perfectly valid. But Java does. It's one of the few things that Java allows us to use some shorthand and say, you know what, you're going to, whatever variable type you're storing the thing in, we're going to assume that that's the type of hash map that you want. It's one thing that Java does infer for us. Usually Java doesn't infer things like that. And honestly, I kind of wish it didn't. It used to not. It was forever ago now, but it was an update to Java where they said, you know what, you ain't got to do that no more. I kind of wish they made us, because it makes it better as an educational language. Or I guess I could just specify my types. It is optional. I could just opt to do it in my examples. And then we're going to add key value pairs using the put method. So this is a reference to a hash map on the heap. We're going to follow the reference and then put a key value pair where we have to match the types of the hash map. So if this is string to integer, I have to have string and then integer. That'll add the key and the value to the hash map. And then get will take a key, has to match the type of the keys, and it will return the value at that key. So this will resolve to an integer, and then we could store it in a value of type int, or a variable of type int. It'll auto box back to the primitive type for us, but this will return an int for us. And then we have our enhanced for each loop. Enhanced, what Java calls them. I just call them for each loops. I feel like that's what every other language calls them. We've seen these, if you took 115 here, you've seen these in Python and JavaScript. When you have, in Python, your for variable name of data structure, and then in JavaScript, you would type out of, actually, no, this is in Python, you would type out in. This is the Java syntax. In Python, you would type out the word in, and then in JavaScript, you would type out the word of. Unless you wanted to iterate over the indices, you would use in. Or the keys, the values, depending on what data structure you're iterating over. In Java, we use a colon for that. So our colon is read as in or of in JavaScript, but in Python. So we're going to say for type, and then any variable name you choose in the hash maps, either key set values or key set or values, and that'll iterate over either the keys or the values of this data structure. Oh, and I'll read my note, I guess. Technically, this doesn't have to be a data structure. It's anything that can be iterated over. Sometimes we'll use these loops for something that is not a data structure. Actually, I don't know if that's true inside 116, but in general, that's true. And then we have a few methods. Key set is going to give us a data structure, actually a set, as the name implies. A set of the keys, and then loop over them. Now, and values will give us just the values. Now, remember, the order is unimportant here for hash maps. It's technically ordered by the hash values of the keys, which is something we're not going to predict. We're not going to worry about what that actually would be. But there's a deterministic order. It's just an order we don't care about. It's going to feel random to us. So key set is going to iterate over the keys, but in some order that might not match the order in which we inserted the values in, and same with values. In your memory diagrams, whatever order is fine, whatever order you choose. If you just choose to iterate over, which I usually do, iterate over the values in the order in which they were inserted, that'll be fine for your memory diagrams. And we won't give you a quiz where it would matter, where it would actually change the result depending on the order of the values. I guess unless you're like printing them to the screen. In this example, it would matter, but we wouldn't grade based on that. And then it's very common, the pattern that I like the most is to iterate over the key set, and then the very first line of my loop, get the value at that key. Now I have access to the key and the value simultaneously, and I have full control over how I want to iterate over this data, how I want to work with it. There is also dot entries if you want to iterate over both simultaneously, but the syntax is a little more confusing than I'd like it to be for 116. If you want to use that, go for it. Even in my own coding, I don't like using it because then I have to remember the syntax. I usually have to look it up because I don't use it often enough. I'll just iterate over the key set and grab the values because I remember how to do that. There's too much stuff to remember in the world these days, especially with programming. Anything that I can ease my memory constraints, I'm going to do. All right, so let's see this in a memory diagram. We're going to use the same syntax as we did for an array list. We have our T chart, except instead of indices, this is going to be the keys and then the values. Keys mapping to values. So we create our hash map. I was feeling 519 when I made this slide. So 519 is the value that's stored in our variable. And that's a reference that tells us how to get to this hash map. And when we put our key value pairs in there, we're going to get our keys mapping to our values. Key to value. And then when we get a value, we're going to get the value at a key. And it's going to print the value at that key. And I'm using... I'll never care if you see the difference of this in memory diagrams, but it's made this way just so the print line looks a little neater on the slide. I used print instead of print line. Print will print without a new line character at the end. That's why this printed on the same line as this right here. If you don't catch that in a quiz, I will not care. I care if you understand how references, heap space, how all the 116 topics are working. I'm not going to be like, oh, you missed. I did print instead of print line. I'm not going to do that to you. There's no reason to do that. I've taken classes where I lose points for things like that, and it's just silly. And then printing the whole thing to the screen. I did print this in the reverse order because I cut and paste what IntelliJ actually printed. So IntelliJ will, in this example, print these key value pairs and iterate over these key value pairs in the reverse order in which they were inserted. Just the way that the keys hashed in the hash map. That's just the way it ended up. So I print them like that just to show that the order is not going to matter. And that's for what it's worth, that's the syntax of how they're going to print out. And I just said all that. Order does not matter. In your memory diagrams, I don't care about order. I got ahead of my slides a little bit here. All right, I do that often, by the way. You'll see me do that a lot. I know all the big key points I want to say. I'm just going to say them. The slides are more, the bullet points here are more for when you're studying the slides afterwards. Less for me to go off of. So we're going to hit our first for each loop. So we're going to create this variable key that is going to be part of the loop. It's just like our initialization statement in our other for loops, our regular for loops. So key is going to be a variable inside this code block, which means it's going to be destroyed afterwards, which is important. It's important that that happens, by the way. I guess not ridiculously important, but it's important here because I am reusing the variable named key. If that variable was not destroyed after this for loop, I wouldn't be able to do this. I would get a name conflict. I would have two variables named key on the stack at the same time in the same code. Well, it gets a little complicated there. They would be in different code blocks. I would actually get away with it. But you can't have two variables of the same name in the same code block. So it's important that that did get destroyed so I can reuse the name. We like having loops where I is the iteration variable. If that weren't the case, if that I didn't get wiped away on each loop, we would have to keep going I, J, K. It'd be, not the worst thing in the world, but that's one benefit that we get, that the variable does get destroyed. And usually you're done, once the loop ends, you're done with that iteration variable. If you want it to live longer, declare it before the loop starts. So the variable goes inside. We're going to iterate over the key set. Here, it will technically be the other order, but my memory diagram, I don't care. I'm still going to earn credit if I do it in a different way than the machine would. And I'm going to print the key, iterate over the next value in the key set, print it. Get to the next loop. That loop's over. Key does not exist on the stack anymore. Value, iterating over the values only. Just printing them to the screen. That loop ends. Value no longer exists in memory. And then we're going to hit our last loop. We're going to iterate over the keys. I'm going to declare a new variable. This variable is declared inside this code block. So it goes inside this code block in the stack. And then get the value at the key. Print everything out. Iterate through the next key value pair. And then that loop ends. Any variables that were declared, including the iteration variable, but also this variable named value, are destroyed after we hit the end of that code block. So all those variables are destroyed. So right before the program ends, there's only one variable on the stack. All the rest were destroyed. So if we use print, the cursor remains in the same line, and print line shifts it to the next line. Yes. Yeah, print line prints whatever you give it and then adds a new line character to the end. Print just prints what you give it. Okay. The lecture took 15 minutes more than it should have. I think this is one of the lectures that usually spills over to the next day. I think this is just too long of a lecture. I don't think I missed my timing. I think I just have too much there. It's a lot to explain references. It takes quite a while. Introducing references for the very first time. Oh my goodness, shut up. And we're gonna have a pretty, I'll sit on this for a little bit. Does anybody have questions on any of that? Because we have a pretty hard gear shift talking about unit testing. I'll give it a second for questions. Where did that even go? Because I think it's because I double clicked instead of single clicking. Oh yeah, and then it returned focus back to, I see. Returned focus back to my browser and covered it up. All right, no questions, moving on. Oh, we did get one. All right, so if we wanted to compare values but still have access to the keys, we would just iterate through the values. Depends what you mean by compare. If you're only interested in the values, that I'll say often in my programming, I'm not iterating over only the values. It's just not that useful in most cases, but I will if I'm doing something like finding the average of all the values, and I don't care about where those values came from. If I'm creating some accumulation, I'm using the accumulator pattern from 115, and I only care about the values, sometimes that's important. But usually I want access to the keys and the values. That third example, the third loop, where I'm iterating over the keys and accessing the values, that's the most common one that I end up using. All right. How do you know if your code's correct? This is a big question we're going to talk about throughout the semester. How do you know if your code is correct? Of course, the answer is going to be unit testing because that's the title of the slides. But let's talk about what that even is and why we use it. All right, so how do you know your code's correct? Well, just submit to Autolab. Autolab's going to tell you if it's right or not, right? Yes, and Autolab is, of course, helpful when you're first learning out, but it's a crutch. Like, it's something we only use for education, and it's only going to exist for education. Nobody in the real world, on the job, your senior devs are not going to be writing you automated grading scripts that are going to look over your code and tell you if it's right or wrong. Before they do anything like that, they would just write the code themselves and save a lot of time. Like, part of writing an Autolab grader is actually doing the solutions. I have to make the solutions to get them in Autolab for the correct... Oh, we haven't actually done any Autolab stuff yet. But But Autolab in this course contains correct solutions that it'll run your tests against. So if I were your senior dev, I would never write you an auto grader. I would just do the project. I would just do it and assign something else to you that you can handle without having an auto grader. It's not going to happen in the real world. So it's a crutch that we use just to help you learn. It's not going to exist out there in the world. So the first thing you've actually done to test your code is to write a main method and print your values to the screen, which is an excellent start. This is something that we struggle with trying to get students to even do in 115 without forcing them to do it. Usually we just got to force them and say, you will write main methods. Students will come to office hours and say, is this right? I'm not getting credit for this. What's going on? And they don't even have a main method. They're not calling their code at all. Just calling your code and printing the values to the screen is a huge first step in testing. I can't believe anybody gets through 115 without ever calling their methods. It's wild. And it's one of the challenges of 115. We work with students and get them to understand the importance of that and how to do it. Some students don't even know how. Of course, they're just learning how to code. But at this point, when we're focusing on how to write large programs, you're outgrowing this at this point. So unit testing is what we want to start talking about in 116, and this is a way to automate our testing. So we want to write code that's going to test our code. That's where we want to be. So with unit testing, we're going to code a series of tests with input-output behavior. For the most part, later in the semester, we'll have some that are actually in task 2, starting with task 2. We'll have some that aren't specifically input-output behavior. We'll want to call a method and then check the state of an object. But we're going to have some test cases and then run that automated test with all those test cases, and we want to call that code correct only if it's correct on every single input. If it always does the right thing on every single thing that we checked, then it passes. And if it fails a single test case, then we're going to say it fails. So we go for perfection with these things. Unit testing has to be perfect. If we expose one bug in our code, we want to fix that bug before we release that software to paying customers, and they get all pissed off because we got all kinds of bugs and our characters in our games are doing backflips and bugging out because we were like, it's probably good enough that we weren't correct all the time. We want to be correct all the time. We do strive for perfection in programming. So let's talk about what this even means. Let's give a concrete example on this. So say you're taking a course. This would be like the very first part of 115, this very simple add method. You're given a task that says, write a method named add5 that takes an int as a parameter and returns an int, which is going to be the input plus 5, which is roughly how it would be worded, how I would word this in a programming assignment. So we have this method. We write this beautiful code. I'm feeling confident about it. Like, yeah, I wrote this method, but not too confident. Like, how do I know this is right? Well, you submit to Autolab, and Autolab gives you credit, and then you're like, yeah, I did it. But how do you yourself know that your code is right? That's where I want you all to be by the end of 116, is how do you write code, and without any external feedback, namely Autolab, how would you know that your code is correct? How would you gain confidence that your code is actually correct? Well, the first thing that you would do, because that is what you have to do before, by the time you graduate, you have to be able to be at that level, which can be scary. I mean, that's tough. But we're taking the first steps in 116. We're taking the first steps today, baby. So the very first thing you would do is write a main method, call your method a few times, print things to the screen, and say, it looks good. Looks good to me. Let's see, add 5 of 2. Should be 7, and I printed out 7. 5 should be 10. 1 should be 6. It looks good. That's fine. And this still, I still use print lines like this from time to time when it's very small tasks that I'm working on. But what happens when you have a program that's hundreds of files, tens of directories, and you have a method that sorts hundreds of songs, and you're printing 100 or 200 songs to the console and trying to figure out if they're sorted in the right order. It's quickly going to become tedious when our code gets large, when we're working with large pieces of data. It's going to be very difficult to test like this. You're very quickly outgrowing calling a main method and printing things to the screen and manually checking with your eyeballs. That doesn't scale at all. So what we want to do is automate this, and that's where unit testing comes in. We're going to write code that tests our code. So let's do this same exact thing that we're doing here, but write it in a way that's automated. So this is exactly what that looks like, and don't worry, I'm throwing a bunch of code at you, but we're going to break it down line by line. So this is going to automate the same main method that we saw in the previous slide, but it's going to automate it in a way that we just click a button and it's going to make sure that everything's good to go. So this is going to go in a separate file. In this class, all of your tests are in a test package, and there are some sample tests given when you first clone the repo for the project. There are some tests already given there, some examples. Task 2 and Task 3 don't have testing. Oh, yeah, I did misspeak earlier. Don't have testing requirements, so not every task has testing requirements. They should have. I should have scaled back the tests that I give you on those ones to ease you into Task 4, which is going to be a lot of testing. But yeah, this is our first automated test. So this will be in a separate file in a package called week 2 in a file named addtest.java, which exists in the Yeet repo. So first, we're going to import the things that we need. So this is our first import. It's our third import total, and it's our first one that isn't even included in Java. We're going to use the JUnit library and import from that library that doesn't exist in Java. If you just create a Java project and try to import this, this line is going to give you an error and say, that doesn't exist. I don't know what you're trying to do here, because it doesn't know where that is. This is where our pom.xml comes into play. That pom.xml says, hey, we need to import JUnit here because our human's going to be using some JUnit. And that is automatically looked at by IntelliJ. It sees that pom.xml. It realizes that this is a Maven project. Maven is the software that's going to read the pom.xml. And then Maven is going to install all the dependencies for you and link them to your project. That all happens automatically. If there are issues, there haven't been issues with that in years. IntelliJ's been really good at when you clone the repo, it just automatically does all that stuff. But if you do create a separate repo, that pom.xml, that is something you'll have to set up. You can copy the one from my repo, but you do have to manually tell IntelliJ to run Maven on that POM file. But it will happen automatically on cloning. So you won't have to worry about it in 116. But if you want to do your own projects after the fact, that's something you'll have to figure out how to do. I can help you through that if you ask, if that's something you're interested in. And then import static. Don't get too bogged down with this. This is just something we're doing to make things a little bit simpler. Import static means import one static method from a particular class. So we're importing the assert true method from the assert class. Assert true is a static method in the assert class, and then we can call assert true just by calling assert true. If we didn't do static, we could do this another way. We could say import org.junit.assert, semicolon, just cut it off there, and then say assert.assert true. That would also work for us to be fine, but just so we don't have to do assert dot, so we don't have to do that every time, we'll import static and then just grab that one method that we're going to use. And then we're going to use this test. So what we imported here from the JUnit library was a test annotation. So this is going to annotate this method. So this annotation says that this method is a test. It's very important to have these. Don't forget your test annotations. If you forget your test annotation, it will not be treated, that method will not be treated as a test, and then it won't be executed as a test. And then when you submit to Autolab, Autolab's going to say, where are all your tests? And just crash and burn. Make sure you don't forget your test annotations. Very important. And the reason why we do this is because we will start writing helper methods in our test classes that are not themselves tests. So we use the annotation to distinguish which methods are helper methods and which methods are actual tests to be ran by the JUnit library. So very important to annotate your tests with @test. It's a common cause of errors. Don't be that person. And then we're going to name each test. Whatever the method name is, that will become the name of the test. So it's helpful to name these something logically. Some of y'all will do test 1, test 2, test 3, or just test and have everything in one test. You know, I'm going to be mad at you. I might give you some attitude if you come to me in office hours and you have an issue directly caused by your naming convention. But otherwise, you know, give these meaningful names, but I'm not going to harp on it. I'm going to call this test add 5 because I'm testing the add 5 method. And I'm only going to have, actually I'm going to have a few tests here. But and these will appear in Autolab. Autolab will give you feedback based on individual tests. It'll tell you which tests performed well or not. By the end of this lecture, by the end of this slide deck, I'll explain more about what you're going to see in Autolab. The feedback that Autolab gives is confusing at first. So we'll take some time to go over it. I think we should have time for that. The third slide deck in this lecture is fairly light, so I think it's okay that we're going over on these first two. Because this one, there's a lot to talk about with unit testing, so I'll take my time on this one. And then finally our test cases. So everything else was just set up, and now we actually get to run some test cases. This is where we're going to automate our testing. So we're going to call assert true, which is going to be a test case that's going to either pass if the expression we give it resolves to true, or fail if that expression resolves to false. And we have to give it a Boolean expression. So I'm giving this a Boolean expression that's going to call the method I'm testing. In the adder class, I'm going to call the add5 static method. And notice that these are in the same package. Just a quick side note. These are in the same package. If they were in different packages, I would have to import the adder class. I would have to import week2.adder. When you're testing in your homework, you'll have to import ratings whatever you're importing, and then call the methods like this. And you could even import static week2.adder.add5, and then just do add5 without the adder dot, just like we did with the assert true. Would be that's an option that you have. So what we're going to do is call the method. And please call the method. A surprising number of times, which is only like a few, like maybe 3 or 4 times, but that's still surprising to me. Students will have issues with their testing because they never called the method that they're testing. You have to call the method that you're testing, or else what are you testing? So you have to call the add5 method. This is the method that we're testing. Call it with a specific input, and then check if that equals the output that you expect. So if I call add5 with 2, I expect this to resolve to 7. So I'm going to assert that the expression that this returns equals 7 is true. So if this returns 7, if this resolves to 7, the expression will be true, and this test case will pass. Same with the other two, and if all 3 of these test cases pass, then the test itself passes, and if all the tests in a test class pass, then the entire test class passes. And we'll see in a minute here that we can have multiple test methods in a single test class. So we have, and then if any one of these fails, if any one of these resolve to false, then the entire test fails, the entire test class fails, the code fails, the code is incorrect. We have a bug that we've exposed through our testing, and we want to go in and fix that bug at that point. We do strive for perfection. 0 bugs is the goal. We never want a bug. especially if we know about it. If we write a test that exposes a bug, we know about a bug, we're going to fix that before we release it to clients. The only bugs that paying customers should see are the ones that we never caught, that we just didn't know about. And ideally, we catch those. And note that there's no main method in this class. The JUnit will run things a little bit differently. JUnit has its test runner, which does have a main method. And then that test runner is going to find this, read the annotations, run the appropriate methods, and do all the things. We don't have to worry about our own main method. It's handled by the library. And IntelliJ plays nice with JUnit. You just run this class in JUnit and IntelliJ. They know what to do. They understand that you're running a test, that you want to run this as a test class. So our big question, this is a big question, is this enough testing? At this point, it's not that big of a question, I guess. I think the answer, actually, it's a little tough with this one. It's such a simple method that you could somewhat reasonably say, yeah, this is enough. But with this method, you could just look at the code and say, yeah, that's enough testing. I looked at the code, it looks right. You're adding 5. In general, this is a huge question. When is testing enough testing? And that answer is going to be different for every developer. Everyone out there is going to have a different answer of how much testing they're comfortable with before they get enough confidence that their code is correct, that they're willing to release it to customers or submit it to their peers for review, for code reviews. Everyone's going to have a different threshold of what they want. In this course, your threshold is pretty clear. It's until my Autolab grader is satisfied. That's when your testing is at least at the minimal. But I do recommend that you, in some cases, going beyond that. There are some. I don't want to get too sidetracked. But is this enough testing? Hopefully with this one, your answer is no, aside from the code being so simple that you wouldn't do any testing at all. But I don't think this is enough testing. So we want to add some tests. We have 3 test cases, and I'd call these like common test cases. These are like the typical ways that your method is going to be called. It's just standard usage. Add 2, 5, 1, 3 small positive integers. It's not that much testing. Your goal with testing should be to this is going to sound redundant, but to test your code, to actually put your code to the test. Your goal should be, if there is a bug with this code, I'm going to find it. And really challenge your code to make sure that it's right on any test case that you can come up with. So for this one, let's try to challenge our code a little bit more and get into what I'd call the uncommon cases. Let's get some trickier ones. We'll get a little bit larger positive integers, but I also want the negative integers. Is it going to be right on negative integers? And specifically when I have a negative, especially when I have a negative integer where the answer is going to be positive, a negative integer where the answer is going to be 0 is a good one. And this is an example of having multiple test methods in the same test class. So to organizing your tests can help you a lot. To organize your tests in a way that it's going to make sense to you. If one of these tests fails, you don't want it to just say IntelliJ to just say your test failed. I'd like to know which kind of category of test cases failed. Was it my regular test cases? If that's the case, then my method's just completely ass broken. But if this one passes and this one fails, I know I have an issue strictly with negative numbers, and I can help that, use that to help my debug process. Yeah, this is not enough. Decimals or strings. Since this does take an int, we do get to scrap some of the test cases. Since Java strongly typed and this method takes an int, X can never be a string, and it can't have decimal portions. So we do get rid of a lot of test cases that we would need in other languages. If you were testing a method in Python or JavaScript, you would have to throw all the invalid types at it. You would have to throw, in Python, the give it none. In JavaScript, give it undefined. Make sure it's robust enough to handle all those cases. That's one good thing we get from Java. We have strongly typed, so it can't take anything that's not an int, or else it'll be a compiler error. That one will catch right away. This method can never be called with something that's not an int. And since we're using the primitive int type, we also can't have this called with null, which would be another edge case that we wouldn't be handling in this particular method. But primitive types can't be null, so we don't have to check that one either. But we do have to check a variety of valid integer values. But that's a good point that there are all the really strange inputs. We should be testing all those as well if they're valid inputs to the method. So negative numbers, we got those. And finally, edge case. Oh, yes, we can have multiple tests in the same class. Damn it, Slide, I already said that. Catch up. And then finally, what I call the edge cases. Well, what are called the edge cases. It's not like I came up with that name. But the edge cases, these are the tricky cases. And honestly, I should put -5 in as an edge case. I would say that one's an edge case. These are the special inputs that only come up once or twice. Like really strange inputs that really test a very particular behavior of your method. So in this one, 0, giving it the value, it'd be possible to mess up an input of 0. So your edge cases are typically these special unique inputs: 0, an empty string, an empty array list, an empty hash map. These are all things that you should be testing for when you're writing your methods. Test those edge cases, anything really unique to the method that you're testing. And then we can revisit the question, is this enough testing? Maybe. Maybe not. I don't know. This one is going to depend. This one, we would get a variety of answers depending on the developer. I would probably say yes, but I would like some larger positive and larger negative integers. And there will be bugs in this code. Like this actually isn't, despite the way it looks so simple. This method actually isn't correct on all inputs. Some of you may be surprised to hear that, I guess. Because there are integer overflows. So if we tested with a large enough integer, this would end up wrapping around in negative numbers. And I don't have any checks for that. I don't have any expected behavior for that. It would just break. If you gave it like the max integer value, it would wrap around to a large negative integer value without any type checking. So we could add a few lines here and say, hey, if we wrapped around, throw an exception, throw a integer overflow exception or something like that. So someone could argue that this is not enough testing and that we actually do have a bug. But I think most people probably going to be okay with this. Autolab would be okay with this for 116 for sure. If this were the method, this is the amount of testing that I would expect you to write for this method. Okay, and your goal is to expose any possible bug. So when in doubt, just write more tests. And it's important not to just write more test cases. When you're testing your code, actually think about this. Try to expose different types of bugs. So we're trying to expose bugs that just flat out bugs that only show up when the values get larger. I should have like 1,000,000 in here too. Make sure that's 1,000,005. Bugs that only crop up when the values are negative. Bugs that crop up on the edge cases. We want to think about anything that can go wrong with the method. Thinking about the whole space of possible inputs and which of those inputs could cause us issues. And then write a whole bunch of tests for them. So not necessarily just lots of tests. When in doubt, just write more tests. But a better variety of tests is important. So if you have 1,000, and I've seen students do things like this before, you could have 1,000 tests, not quite 1,000, but you could have 100 tests. I've seen students with 100 tests and still failing Autolab saying that their testing wasn't good. But they'll have 1,000 tests where they're all positive integers. They tested like values 1 through 1,000, and never tested a single negative number. So it's not just lots of tests, but lots of variety of tests. You get a lot more mileage out of a variety of tests than just a lot of tests that test the same thing. You're looking for possible bugs. What test case is going to expose a bug that might exist in this code? All right, let's do a quick demo. With the same. Oh, yeah, because let me close the other one. Like, why do I have two of these open? It's because I demoed cloning last time. So we're already in week 2. So here's the code that we just saw on the slides. And we could add more test cases. Let me add that million that I was talking about. And what we want to do is run these tests. So I have my adder. Same code that we saw in the slides. And I have my add test. Same code that we saw in the slides, except I just added that 1 million. And when we run this code, it's the same way that we would run any other code. I guess a little bit of difference here. If we want to run one individual test method, we can use these arrows. Be careful with those. I've seen students, and I've done myself, honestly, accidentally just running one method instead of running the whole test class. So you could run the whole test class with this button up here, but just to make sure that I don't get any confusion, these days I've learned my lesson, and I go over here and I right-click the file name and go to run, and run the whole thing. I know that's going to get all of my test methods, and I'm not going to accidentally click the wrong arrow over here. And this is what you want to see. A bunch of green check marks. This means all 3 of my test methods passed, and my entire test class passed. And when you pass, there's not much information that it's going to give you. But if we go into adder and say we did implement this incorrectly, and now I can run my test again like this, but once you run something, you can use the run button up here. What this will do is run the last thing that you ran, or you can use this drop down, which is like a history of all the things that you've ran. I can use this now, which is helpful because I'm debugging this code, but I want to run code in a different class. And now I have errors. I have tests that failed. All 3 of my tests failed. And I can click, and now I get some information. It says assertion error. That means that the test failed. And it gives me the line number where it failed. So line 11, the very first test case, this one failed. On add 5 of 2, it did not return 7. And I'll show this in the slides, but what we can do is add some hint text here. What I would do here is add some hint text. Oh, that's a little awkward. And this text will be printed if the test case fails. So if the test case fails, this is the information that you'll get. So when I go back there, returned 6. So I'm expecting 7. It returned 6. That's bad. That's bad news. I got some code to fix. Then I can go to adder, try to figure out why this would return 6 instead of 7, and fix my code. Once we fix the code, we should get our green check marks again. And when the test passes, we don't get that hint text printed to us. When testing an empty arraylist, you would do the new arraylist R1 and then set it equal to a new arraylist. You would still do new arraylist. If the code you have there, just semicolon after R1, that's going to give R1 a value of null, which generally in 116, oh well, actually always in 116, I don't expect you to do null checks. Until we get to linked list, I guess. Linked list, we will do null checks. But if a method takes an array list, I don't expect you to test it with an input of null. Though I maybe should. I don't know. It would just be a little bit of extra tedium. But you would set that equal to a new array list and create an actual array list, a reference to an array list, but the array list happens to be empty. All right, end of demo. So that was our demo. Let's talk about a few special types that we want to test. Testing strings. I gotta make sure my timing's right. Okay. Yeah, we should be good. Testing strings. This is a special thing that we test. This test fails. So we have our same setup, the same structure and everything. Probably should have done this in IntelliJ while I was over there. You know what? Let's do it that way. I gave the spoiler anyway. No, I have too much crap here. So this test, I have the string AB. I'm calling dot strip was going to remove leading and trailing white space. So string A and string B, or string 1 and string 2 will both be AB, the strings AB. They'll be the same exact strings. I'm going to assert true that they equal each other. I'm going to run this test. I'm just going to run this one test method because I have a bunch of other test methods in here. And these are not equal. These are not the same string. I'm gonna sneak this one in here. I'm gonna run what's called the debugger. I will talk about this a lot later in the semester, wherever I can find time. But I can run the debugger that will actually show me the values of string 1 and string 2. We can verify that they are the same exact values, but this conditional resolves to false. This Boolean expression resolves to false. So why is that? That's weird. Let's talk about why that is. So this resolves to false. My short explanation for this is strings be weird. The longer explanation is strings are immutable. They are actually references to objects on the heap, and not values on the stack like we're showing in our memory diagrams. And when you use equal equal to compare two objects on the heap, by default, the default comparison is to compare them by reference. Meaning, if string 1 and string 2 refer to the same object or not. So if they don't refer to the same object, which they don't in this example, then this resolves to false. It only resolves to true if they refer to the same object on the heap. Actually, not even by default. That's just how equal equal works with objects, isn't it, in Java? I'm thinking of Scala. Scala was a little bit different. But this will compare them. Are these referring to the same object? It's just it's checking. Is the value of this string equal to the value of this string? And the values are actually references, so it's just saying, are these the same reference? And they're not. That's why I do the dot strip. Just the way that this is set up, they are going to refer to different objects. It's not always the case. Sometimes you will get away with this. It just depends on how the strings were created. The answer is to use dot equals on our strings. Don't use equal equal. Use dot equals, and this is actually going to compare the values of the strings instead of the references of the strings. So when comparing two strings, use dot equals. If you don't, and I don't care too much about you understanding the reason why, not quite yet in 116. I would expect you to understand that later in your careers. But for now, use dot equals, not equal equal when comparing strings. That will compare the actual values of the strings. Then our hint text. I already talked about the hint text in the demo, so I'm not going to belabor it here. I do recommend this. A lot of students in office hours won't have their hint text, and then they'll ask for help, and one of the first things I'll say is add your hint text. Like, what, you don't even know what's going on. Check what's going on. So this will be printed if this test case fails, and it's called a hint text because it gives you a hint as to why it failed. So strings equal, this is terrible hint text. It doesn't tell you anything. This would never be my hint text. My hint text would be like string 1 equals, and then the value of string 1. String 2 equals, and then the value of string 2 would be good hint text here. That can really help you debug, though. All right, and let's jump into another example. So we saw this code last time that computes your letter grade. Let's expand this a little bit. We'll write another method that computes your plus or minus modifier. So we're going to do this similar to doing the tens by using integer division and getting the tens digit and checking the tens digit. But now we're going to get the ones digit. For that, we're going to use the modulo operator. If you haven't seen this, I think we see it briefly in 115 these days. But a refresher is that this is kind of the exact opposite of integer division. This is only going to return the remainder. So score divided by 10 and give me the remainder and put the remainder in this variable of ones. So we're going to take score, like when score is 95, we're going to divide it by 10, throw away the 9, and just give me the remainder, which was 5 in this case. Store 5 and then check. If it's greater than or equal to 7, we're going to give you a plus on your letter grade. If it's greater than or equal, greater than 2, but less than 7, we're going to have no modifier. Else, it's going to be less than 2, and we're going to give you a minus on that. And this is our grading structure for this fictitious course. And we're going to test this. Here's our main method. We want to code that up in a actual test. We're going to test just the plus minus method for now. We're going to call plus minus of 95. We get whatever the result was. When I'm going to start truncating my classes, once they start getting bigger, we would have the package declaration and any imports, importing assert true, importing the test annotation. I'm going to start trimming them down. We talked about package and imports. We're beyond that now. And then we're going to check. This is the plus minus for 95. We expect that to be an empty string. There's no modifier. So we're going to assert that PM dot equals, not equal, but dot equals the empty string. And then if it's not, we're going to give a little bit of hint text. So with 95 as an input, there should be no plus or minus, but this is what we got, and then give us what the PM was. 78, we're going to code another test case. We expect that to be a plus. 78, it should be a plus, but this is what we got. The hint text is giving us more clues as to what could go wrong. It gives us the information that we need, specifically what PM actually was. And then 51 should be a minus. Tell us what we got. So this code passes. We run this test case. The code passes. And we're like, oh, cool. 3 test cases. We passed them all. Feeling good, right? But this is where we would want a lot more testing. I'm not going to show a full test suite with all the different test cases that we could give this. There are actually quite a few things wrong with this code that, oh shit, we actually won't revisit this one. That had to get cut for the summer course. But in the main semester, I revisit this and fix all the bugs with it. But there are bugs, one of them that we would expose. Let's add one more test case. 100. If I got 100 in this course, I want my A+, damn it. Our code is going to fail this last test case. We're going to get a hint text that said 100, it should be plus, got, minus. This student is going to get an A- if they get a 100 because of the way that we set up our code. 100, when we take that modulo 10, let's get the code back up here. We're going to take this modulo 10, which is going to be 0, which is going to hit our else, which is going to be a minus. So we got a pretty bad bug here. I don't want students who got 100% getting an A- in the course. They're going to be pretty upset, and rightfully so. That's a huge bug. So we're going to add a little bit extra code to handle this edge case. This is an edge case that one particular input that's going to expose that bug. Making sure you hit those edge cases is very important. We've got to hit that edge case to expose that bug that can exist. So when we're writing tests, we're trying to expose any bugs that might be out there. And this test case is going to expose the bug and give us clues as to how we're going to go and fix that bug. So we know on 100 we're getting minus. We can trace through our code and say, why would our code be given minus? And then say, oh shit, yeah, it does. And then go in there and fix the bug, run our test again to make sure we didn't break anything else. One of the very handy things about automated testing is when you make a change, rerun all your tests and just have it automated so it can check everything. It's common in industry when somebody makes a change to a code base, run every single test in existence on that code and make sure they didn't break anything at all. And having that just all be automated is, I mean, life-saving, career-saving at least. It'd be a pain if we just had really mysterious bugs that crop up and we don't even detect them. In testing doubles, this is very important as well. Possibly more important than the strings, at least in this class, is testing doubles. This test fails. We have 0.3 equals 0.1 times 3.0. So 3.0, if my math is right, I'm going to multiply this by 0.1. This is going to resolve to 0.3. I'm going to check if that equals 0.3. That should be true. And then in the real world and in the mathematical world, that's going to resolve to true. We're going to assert that it's true. It's going to be true. Everything's good. In the world of computers, not so much. In the world of computers, this gets us in big trouble. This is disastrous. It will catch up to you. Why was my stream lagging? Was anything lagging for anyone else? Hopefully that was just a me issue. So if you print, and you can do this, you can run this code, just print 0.1 times 3.0 to the screen, and you'll get this. It buffers for a few seconds every once in a while. Oh, damn it. I wonder if that's because I went to low latency. That sucks. Drop frame 0. To lead me to believe it's on third time in 2 hours. Okay. Yeah, as long as it's not happening all the time. I might go back to regular latency on the next one. I'd assume that's why it's happening. I do like the low latency though. When chat's like 10 to 15 seconds behind me, it gets weird. Okay. So if you print this to the screen, you're going to get this, which is pretty much 0.3, but it's not equal to 0.3. It's not exactly 0.3. So that's why this is going to be false. This does not evaluate to 0.3. It evaluates to something that's pretty much 0.3, but not exactly. And equal says, are these two values exactly equal? And they're not. So the reason for this, which I foreshadowed in the last lecture, is because doubles are stored using a 64-bit representation, and 64 is less than infinity is the important. 64 is a finite number, which is the important part here. So it must be, some values must be truncated to fit in 64 bits. Sometimes 64 bits just is not enough space to store certain values, and 0.1 happens to be one of those values. So let's do a quick overview, possibly refresher. I don't know where you would have seen this part of things before, but possibly refresher or a very brief intro into how fractions work in binary. So in binary, if you have like the binary value 1, 0, then that would mean 1 in the 2's place and then 0 in the 1's place. If you had 1, 1, 0, it'd be 1 in the 4's place, 1 in the 2's place, 0 in the 1's place. Everything's just powers of 2, similar to powers of 10. We have the 1's, 10's, 100's, 1000's place. Same thing with 2's. That also extends in the decimal direction. So I'm hoping that basic binary everybody's familiar with. If not, the takeaway here is that doubles get truncated. But this is just the explanation of why that happens. So this works in the decimal portion as well, where we would have in decimal, we would have the tenths place and the hundredth place. It's the same thing with twos, except by powers of 2 instead of powers of 10. Instead of 1 over 10 to the 1, 1 over 10 to the 2, 1 over 10 to the 3, it's 1 over 2 to the 1, 1 over 2 to the 2, 1 over 2 to the 3. So this is the 1/2 place, 1/4 place, and the next one would be the 1/8 place, then the 1/16 place. So 0.11 in binary is 1/2 plus 1/4, which is 3/4. So 0.11 is 3/4 in binary. In decimal, there are certain values that cannot be represented without truncation. The value 1/3 can't be expressed in a decimal portion. It's an infinitely repeating decimal. We can't write down exactly 1/3 in decimal, doing 0.3 out to infinity. It would take infinite digits to be able to exactly store this as a decimal. And the same is true in binary. Values like 0.1 in decimal, 1/10, cannot be represented as the sum of powers of 2 in binary. So 0.1 in base 10 would be 0.000110011 repeating forever in base 2 in binary. And at some point, which is 52 bits, the computer's just going to stop writing digits. So it's going to truncate that to 52 decimal places. Well, actually, it would be right here, point, and then 52 after that decimal point, and then the scientific notation. This is basically, I didn't explain this, but this is basically scientific notation. This is the actual decimal value, and then this is the exponent. So this 1 point this times 2 to this power, and then 1 bit for positive or negative. So we can't represent 0.1 in base 10 exactly in base 2. We just can't do it. It would have to repeat forever. We can't do it. So we have to truncate. At some point, we just truncate it, delete everything that comes after, and we get something that's pretty much 0.1, but not exactly 0.1. All right, so what do we do about this? Like, this is a problem. So what do we do about this? And what we do is allow some tolerance when we're comparing our doubles. We don't want to just say, are these doubles equal to each other? For our purposes in 116, this is important for our testing. When we test, we want to make sure a method that returns a double returns the correct double, and we can't check it for equality. We have to allow some tolerance. But this is also important if we have a conditional, like outside of testing, if we have a conditional. If this value that stores a double is equal to 2, I want to run this code, else run this code. You can't do equal there as well. You have to give some tolerance if you want to do those kinds of checks. Or else you're running the wrong code, you have a serious bug, things are going wrong. Same with inequalities. If a value's less than or greater than in double land, the difference between less than or less than and equal to when you're comparing doubles, it's probably the same exact thing. Because you're not going to have two doubles that are equal to each other. You'd have to do less than and then some tolerance. But anyway, what do I mean by tolerance is we're going to make sure that the values are equal within some value. So I like to create this as a constant. So unintentionally, I guess, this is our first private variable. Private meaning I only need this variable inside this class. I don't care if anybody in the outside world has access to this. I'm only using it for this test class. Final means it's a constant. The value can't change. And then the rest is stuff we've seen. It's going to be of type double. And then the name of the variable, when it's a constant, naming convention says, let's make it all capital letters to communicate to other devs that it's a constant. And then set it equal to some value, which for our purposes is the amount of tolerance I want to allow. So for this test case, I'm going to say when I compare two doubles, I want to say that they're equal to each other if they're within 0.001 of each other. And the amount of tolerance you allow can be different depending on the application that you have. Sometimes you want larger, sometimes you want smaller tolerances. For 116, usually I think 0.001 gets you through the entire semester, if I'm not mistaken. But in general, outside of 116, you should really think about what kind of tolerance you want to allow. And then I'm writing a helper method. So I have a method without the test annotation that's going to compare doubles for me. Take two doubles and check if they're within epsilon of each other. So for that, I'm going to subtract them. That's going to give me the difference between these two values. But this difference can be positive or negative depending on the order of the doubles. And I don't want to have to check in both directions. If D1's larger, this is going to be positive. If D2's larger, this is going to be negative. But I'm only concerned with the magnitude of the difference. So I'm going to take the absolute value of the difference. That gives me the magnitude of the difference. I'm going to make sure the magnitude of the difference between these two doubles is less than epsilon. If it is, those doubles are equal to each other according to my test. They're close enough to each other that I'm going to say, yeah, they're equal. So in this way, we're ignoring truncation errors, which are errors that are caused by that truncation effect. We're eliminating those errors by allowing this little bit of tolerance. So now when we run our test, we're going to call our compare doubles helper method and say, is 0.3 close enough to 0.1 times 3.0? And this epsilon is large enough that it's going to ignore that truncation error. It's going to ignore the fact that this isn't exactly 0.3, but it's close enough. It's within 0.001, so for our purposes, we're going to call them equal. They're equal with some tolerance. They're within 0.001 of each other. When you're doing this, don't forget the absolute value. It comes up every semester. I have at least one or two students in office hours who have D1 minus D2 less than epsilon, and I don't know, don't be that person. And then I have to do the whole negative thing. They'll have a situation where D2 is always larger than D1, and they'll have like 1 minus a billion less than epsilon, and it's going to be true, but those values are very different. But the subtraction, the difference, led to a very large negative number, which is, of course, less than 0.001. And then I realized that the student did not internalize this lesson. They just cut and paste my code. And then it's usually in the second half of the semester I see those errors, because they were just cut and pasting my code, and then they pasted it wrong. Like, I don't know. It's important that you understand the lesson. But yeah, that's comparing doubles, testing doubles. Oh, I got way ahead of my slides. I just went through the whole thing, didn't I? I think I said all this. Oh, yeah. Oh, I even added a bullet point. I got so sick of seeing that in office hours, I did even added a bullet point for it last semester. I forgot about that. All right. So now let's talk about what you all came here for. What's Autolab gonna tell me? When I make a submission, what's Autolab going to say? And how do we make some sense out of that Autolab feedback? We'll probably have a Piazza post on this as well. We have a Piazza post that we like to cut and paste each semester. I forgot to so far, but we'll add that as the questions about this start coming in, as y'all start working on task 1. So, when you make a submission to Autolab, it's going to test 3 different things. 3 different tests are going to be ran on your code, with the exception of task 2 and task 3, because there's no testing requirements, which I should have just added them, but next semester. All right. So when you make a submission where testing is required and coding is required, what Autolab's going to do is it's going to run your tests in 3 phases, and this is pasted in, this is in the document too, but it's confusing enough that it's worth spending some lecture time on as well. That it's going to take your tests. I have students even at the end of a semester who are still not quite sure what's going on, but what Autolab will do is take your tests. It will ignore your code at first. Anything in the ratings package, it will ignore all of that. Won't even look at it. But it'll take everything in your test package. It'll take your test class. And then on Autolab, there are multiple solutions. There's one correct solution, So a solution to the task, programming task that is correct. It will return the correct output on every single input, and a variety of incorrect solutions, all on the server. So there's a whole bunch of solutions on the server. One of them's correct, and the rest are not correct. Autolab will take your tests, throw away your code, take your tests, and run your tests against the correct solution and the incorrect solutions. And your test suite needs to be thorough enough that it looks at the correct solution. First, it needs to be correct. Your tests should be checking the right things. So to run against the correct solution, and if your test fails a correct solution, that means there's something wrong with your tests. Your tests are getting a correct answer on an input, and your tests are saying, no, that code's wrong. If that's the case, then the testing shuts down. It says, hey, you're wrong on a correct solution. Fix your tests. If you're right, if you pass the correct solution, your tests running against a correct solution, I think that's what trips people up, the way I word that. So I'll take a correct solution and your tests and smash them together and then run your tests. So your tests and some code you've never seen before is going to be married up with that, and then your tests are running and your tests are checking the correct solution. Your test cases are running against that correct solution. And then I'm going to take that correct solution away. I'm going to take an incorrect solution, smash it into your test suite, and run your tests again with the incorrect solution in place of your code. Then put another incorrect solution, run your tests again, another incorrect solution, run your tests again, and then do that for all the incorrect solutions. And your code, your test should be robust enough to identify every incorrect solution. Say, all those solutions that you just gave me, they were all incorrect. You need at least one test case, and this is where that perfection comes to your advantage. You need at least one test case. You could have 1,000 test cases across 100 test methods. You need one test case for each incorrect solution, one test case that's going to fail that incorrect solution, and then you've correctly identified that incorrect solution as an incorrect solution. Your tests were thorough enough to say, hey, that one's wrong. I got this test case here, and this input didn't give me the right answer. That thing's wrong. That's what your tests need to do. And then if you get through all that, then we throw away your tests, bring in your code, bring in my tests, marry them up, and then run my tests against your code to test if your code is correct. So those are the three phases. Test your tests on a correct solution, test your tests on incorrect solutions, and then test your code using my tests are the three phases. So that's how we're testing in Autolab. When you get your feedback, I got credit for program test 1, yay. So when you get your feedback, it's going to show in those three phases, running your tests on a correct solution, and it's going to give the test names. These are the test names that I have in my code. So this will show you your test cases, whatever method you have, and this is why I recommend breaking it into separate test methods, because Autolab will give you feedback on a per test method basis. So you can tell if there's an issue, which one is the issue. If you have all your test cases in one giant test method called test the thing, you're just going to get test the thing failed, test the thing passed, and it doesn't give you as much information as you might like. So if you split them up into different methods, you'll get more feedback from Autolab. So I have all these tests in my test class, and they all passed a correct solution. If any one of these failed a correct solution, this would be the end of the feedback. This would be a sad face, and that would be the end. It would say, fix your shit. I did pass all of the correct solution. Every test case that I gave it, I did say, yep, the correct solution did do the correct thing. Then, so I moved on to the incorrect solutions. I have this incorrect solution called average bad on large lists. Each incorrect solution is going to have some cryptic name. The names aren't intended to be understood, but they're intended if you're having an issue with an incorrect solution, the name might give you a little bit of a hint as to what might be going on with that. I see way too many students trying to reverse engineer these test names. I mean, you're allowed to do that, but it's a strategy that usually wastes your time. It wastes students' time because it takes longer than just writing good tests. But average bad on large list. So the average method is bad when the list has enough elements. So really what I'm making sure is that you have at least one test case that's going to test a large list. Test the average method on a list that's sufficiently large. If all of your test cases are like 2 elements, you're not going to reject this one. So I have a whole bunch of test methods here. Most of them did not reject the solution. So this incorrect solution passed all of my tests, all of these tests, and all of these tests. But it did fail my test average method, which is the only one that I would expect to fail this one. It's the only one that had a chance. This one successfully rejected the incorrect solution, meaning I have at least one test case in test average where I had a list large enough that it identified this bug. There's a bug in this code, and that test said, hey, there's a bug in this code. Identified that that's an incorrect solution, so I was good on that. As long as at least one of your test cases fails the incorrect solution, you're good on that incorrect solution. Another incorrect solution, I had test average. This is another average one, my test average took care of them. So I correctly rejected those incorrect solutions. Digits, no negative. My test sum of digits successfully rejected that solution, so I'm good on that. Doesn't matter if all of my other ones passed it, that's fine, as long as one of them fails it. Digits off on 0. Test sum of digits, rejected that one too. Digits, only 3 digits. Test sum of digits, got that one too. Key bad on empty, which is a little more cryptic now. I guess it's not too cryptic. My test best key empty, got rid of that one. It's an empty hash map. I guess it's pretty clear. At least I think it is. Hopefully it's not too clear because I don't want these to be very clear. Just reverse engineering everything. Key bad on multiples. That one's a lot more cryptic. Successfully rejected the incorrect solution. Cool. So I had this test case. Got rid of that one. And then key bad when best is negative. I had test best key 3. Got rid of that one. And it passed my other key tests. But it did fail on this one, so I'm good. So I rejected all of the incorrect solutions. I have at least one test case that got rid of each one of them. And then finally, the Autolab test running against my code, which the tests are the same because this is my submission, I have the same tests. The tests I use to test my code, I use those for the Autolab tests. So it gets a little weird there. But these will be your test cases for everything we just went through, and these will be my test cases. So you'll see test best key 1, 2, 3. You'll see these exact ones only for testing your code. So my tests passed everything, and now testing my code with the tests that are in Autolab, I passed all these tests. So since I got through all 3 phases of testing, my test against a correct solution, my test against incorrect solutions, and Autolab's tests against my code, I've completed the programming test, and I get a score of 1.0 to say that I've completed that task. So hopefully that clears things up more. I'm sure I'll still get questions. I'll handle them as they come. And a lot of questions you won't even have until you start making submissions. Which again, I recommend you do soon, like today. It's going to be way too easy to fall behind. I am worried for you. I'm nervous. Not going to lie, I'm a little nervous. It's going to go fast and students fall behind in the regular semester. All right. So I don't fall behind. I got to keep moving forward with lecture. Let's talk about recursion. Start soon. I would start right after this lecture. And I will have office hours after this lecture. So if you're having trouble getting started, especially if you have Autolab issues are very common. We've been handling some of the questions on most of the questions on Piazza. How am I trying to word this? Most of the questions on Piazza have been just setup issues. If you have those issues, come to office hours. I'll be in the Zoom meeting not right after lecture, but shortly after lecture, 2 to 3. Do we have lab? They don't really schedule a lab section in the summer. I don't know why. Like, it's technically lecture and lab, but the sum of the time of lecture and lab is still less than the sum of time of just lecture during a regular semester. It's 2 weeks short of just lecture. Like, they don't give me any time for lab, so there's no actual lab. I just treat the 11 to 140 block as one lecture, or else I would never get through everything. There'd be absolutely no way. It'd be half a semester of material. So it's just all lecture. One lecture is from 11 to 140 is the same. My math is a little off here, isn't it? It is 10 minutes more because I'm not taking that 10-minute break, I guess. But it's 10 minutes. Should I be ending at 1:30 then? Is the same as a full week of lecture. A normal semester is 14 weeks of lecture, and this semester is only 12 lectures. And I also have to schedule exams during lecture time. I don't have a final exam time. There's just actually less class meeting time by a lot too, because usually we have 2-hour lab each week as well. We do have lecture during quiz days. Again, I can't fit everything in if I don't. So quiz is going to be the first hour of lecture, and then I still will use the rest of the time. Mostly on quiz days, my intention is to have lecture be homework, like tips, tricks, hints, anything I think will help you all get through the homework. Okay, but yeah, let's go. Let's do it. Yeah, there is. I was miscounting a little bit. That 10-minute break, that is accounted for. That there is 10 minutes extra compared to a week of lecture, which doesn't make a big difference. Assuming I don't take that break, which I don't intend to. I mean, if y'all want me to stop for 10 minutes in the middle of each lecture, I don't know, create a poll on Piazza, I'll respect the results of a poll. But whenever I do a vote, whenever I've had a vote like this, everyone says, nope, just go right through. We want to rip the Band-Aid off and get it over with. And especially when it's recorded on YouTube and you can always rewind and everything, you can just make your own breaks. You can just pause me and come back in 10 minutes. You just would be behind chat. Would be the big issue. All right. Recursion. This is our first intro to recursion. This will come back when we talk about linked lists, which will be all of 1 week from today. Recursion is going to be a topic that's going to crop up a few times throughout the semester. So let's get a brief, gentle introduction to it today. So recursion, it's a method that calls itself. End of definition, that's what it is. It can be applied to functions as well, but since we're in Java, it's just going to be methods. So a method that calls itself is a recursive method. And that's it. That's what recursion is. Technically, you know what recursion is now. There's so much more to it than that. And recursion is what I call a slippery topic. It's one that doesn't make sense. And then you study it for a very long time. You think about it for hours. You study it. You reread and search up information about it. And then it doesn't make sense. And then you think about it some more and you write some recursive methods and you get some recursive methods working and it still doesn't make sense. And then you give it a few years, you get some more practice with recursion, and then it still doesn't make sense. And then one day it just snaps, and then all of a sudden it just makes complete sense. But it's one of them topics that just takes a while to sink into your brain. Or at least it took me a long time, and anybody I've asked, they've had a similar experience, where it just takes a long time for it to actually click and actually just make sense. So just to set the expectation, by the end of 116, I don't expect you to fully understand how and why recursion works. But I will expect you to be able to write some recursive methods and get them to work eventually, even if you don't fully grasp the full beauty of what recursion is, how it works, what it does. For me, it took until I think I was a grad student, or maybe in 331. No, I think when I took 331 is when it made sense. In my junior year, that's when I'm like, whoa, that's what recursion was doing that whole time. So we're going to give our gentle introduction to recursion, which will... It's also a deceptive topic. I think this lecture, I think it's gentle enough that it makes sense, but to fully grasp recursion, like to write recursive methods, is a lot trickier. Yeah, and through 31 too. Nice. Yeah, that's when you're writing proofs. I think that's what did it for me. Writing proofs on recursive methods that they were correct, and then analyzing their runtime and everything. Once you're at that deep of analysis of recursion, that's where it got the click moment for me. Yeah, and then getting to the point where you can explain it too. Oh my goodness, explaining recursion is. I think I've got a pretty good strategy for it, but it's tough. So we're going to define this add method. This add method takes two ints and returns an int. And what I want this to do is add two numbers together. This is an example of where our testing could go, where our testing is more important. Like you would have this, if you're actually writing this method, you would just say return a plus b. But somebody gets a little too cute with things and defines it like this. This is a method where you would want to run some automated testing, have a good, nice test suite, check your edge cases and everything. Because this smartass developer who writes this bullshit, you're going to want to make sure that this is actually right. You don't immediately have confidence that this is correct just by looking at the code. You would want a nice test suite with every possible combination of types of inputs that you can think of, and gain your confidence that way that it is actually doing what it's supposed to be doing. So we have this method named add, and during this method, we're going to call a method named add. And these are the same method. So this is a method that calls itself. So when we're running the add method, part of the definition of the method that we haven't finished defining is going to be defined by its own definition. It's really weird. It's messed up. Your first time seeing recursion, it is a mind trip. Which this might be your first time. I don't know if you've had exposure, who's had exposure to this or not. This might be your first time. It's trippy. It's a method that calls itself. So it is a recursive method. And that's about all I'm going to explain about recursion itself, the topic. If I try to explain it, just historically speaking, when I've tried, it doesn't make sense. So we're going to use a memory diagram instead. I'm just going to do a memory diagram and walk you through the steps of this method and show you that this actually does, on the input 4 and 3, this actually will return 7. I had to think about my math. 7. Yeah. This will actually return 7 and print 7 to the screen. So instead of trying to explain why recursion works, how magical it is, how recursion leverages the stack to keep track of variables in a really cute, fancy way, instead of explaining it that way, I'm just going to show you the example of what actually happens when this thing is ran. And this is another shut your brain off moment if you're doing this memory diagram, and we will give you recursive examples on a quiz, probably on quiz 2 on linked lists. I think would be the first time. I don't think I'll get cute enough to put it on quiz 1, but quiz 2 would make sense to put it on linked lists. It's a kind of turn your brain off a little bit moment, and when you hit a method call that method with a stack frame. Somebody made a Piazza post during lecture. You could have asked in chat. When are quiz days? Gerline, go yell at that student. No, you don't yell at them, but like, what the fuck? It's on the schedule, and this is during lecture. So when we run we start easy enough, not simple enough, but familiar enough. We start with the main method. We're going to put a variable named result on the stack. We're going to put a stack frame for add, label it as add, solid line for a stack frame, return arrow goes to the variable where the value is going to be returned. And then add is going to be called with the arguments 4 and 3. The method has parameters A and B, so A and B get assigned 4 and 3. You're going to reply to them. Good. Oh, I don't even understand that. Actually, no, they at least were in chat. They posted anonymous, so I won't call them out, but I guess I did narrow it down accidentally. So we have the stack frame on the stack, and we're just going to go through our code one line at a time. It's a conditional. We understand how conditionals work. So if b equals 0, which is false, we're going to move on to the next conditional. Else if b greater than 0, b is greater than 0. So we're going to hit this line. And here's where it's magic. It feels like magic. Recursion is kind of magic when you first see it. But what we're going to do is pretend that this is just a regular method call. We're not gonna treat it as something special. We're not gonna treat it as recursion. We're just gonna say, okay, we're calling a method called add with these arguments. We're gonna do the same exact thing we did down here when we came across a method called add with some arguments. We're gonna put a new frame on the stack. We're gonna give it the name of the method. We're going to get our parameters on the stack inside that stack frame, and we're going to assign them the values of the arguments. A, this was inside this stack frame, so A is 4 plus 1, so the new A is in the next stack frame is 5. Then B in this stack frame was 3 minus 1. B in the new stack frame is going to be 2. And then our return arrow, whenever we have recursion where it's returning to another stack frame, like this return value is just going to be the return value of the other stack frame, we'll draw the return arrow to the other stack frame. Since we're not storing the return value in any variables, we're just giving the return value to this method, and then that method's going to return, that stack frame's going to return it back to result. And then we start the fun again. Now this stack frame is still sitting right here waiting for its return value. So we still have a stack frame that's sitting right here. We still have the main stack frame that's sitting right here. And we have the active stack frame that's on the top of the stack that's starting the method over again with new parameters, new values for its parameters. And then we're going to run through again. If b equals 0, false. Else if b greater than 0, true. We're going to hit this line and start the process over again. This stack frame is going to pause right here. It's going to become inactive, and it's going to be waiting for the next stack frame to return. So the next stack frame is going to get 5 plus 1, 2 minus 1, 6 and 1. It's going to do the same thing. It's going to do the same checks, get to the same part of the code, and then make another stack frame. So we're going to get another stack frame with 6 plus 1, 1 minus 1, 7 and 0. So in this stack frame, we're going to check if b equals 0. And this condition is finally going to be true. So this is where we're going to hit something called our base case. This is any situation where a recursive method is called where it doesn't make an additional recursive call. We always have to reach a base case, or else every method call is going to create another method call, and it's going to be stack frames all the way down, and we're never going to end. It's just not going to end the method call ever. So we have to reach a base case, and now that we have, oh, I don't want to do that click. Now that we have, we're actually going to return, actually I do want to, let me set on this slide for a while. I got a lot to explain here. We're going to return this value of A, which is 7 in this stack frame. We're going to return that back to the previous stack frame. This stack frame will be popped off of the stack, so the stack frame underneath it is going to become the active stack frame again. That stack frame was sitting right here waiting for its return value, and then it's going to return that value. So at this point, we have 3 frames remaining on the stack. We had a total of 4 and 5 if you count the main stack frame. But we have had 4 recursive calls, 4 calls of the same method on the stack. And this is how recursion works. We make one call. That call is going to make another call, which can make another call, which can make another call. It can go as far down as it needs to until it hits a base case that doesn't make another call. The base case is going to return and let the next stack frame finish. So this stack frame depended on its own definition. but it depended on a part of the definition, namely the base case, that doesn't make another recursive call. So for this stack frame, it depended on its own definition, but a different portion of the definition that's not recursive. So it actually got to finish and return, even though it's based on its own definition, it's not based on the recursive portion of the definition. So now that that actually ended and returned, now this stack frame is going to return this value 7 back to the previous stack frame. So this stack frame will get control again. It actually depended on a recursive call, which was recursive. It depended on the recursive portion of this method, but that recursive portion depended on the base case portion. So it actually got to finish its recursive portion and return the value 7 back to this stack frame. This stack frame gets the value 7. This resolves to 7. And it says, oh, all I'm doing with that is returning it. Returns it back to the previous stack frame. This stack frame gets control of the program again. So we're back here. We called add of 5 and 2. We got our return value of 7. And all we're doing with that return value is returning it. So we're going to return that back to the main stack frame. And result is going to finally get that value 7, which was generated way down here in the base case, returned up the recursion, and finally got that value 7. And then we print it to the screen. Okay, that's your first recursive example. So even though the definition depends on its own definition, we eventually got that definition down to the base case, which allowed us to end the insanity and start returning back up the recursion. Yes. So a recursive method will always call itself until it makes a call that doesn't make another recursive call, and we call that the base case. And we have to hit the base case to be able to end the insanity. So when you're writing a recursive method, I don't think I put these slides in this slide deck. Oh yeah, interpretation versus compilation. But when you're writing a recursive method, I have my 3 ingredients to writing successful recursive methods. My recipe for recursive methods is 1, have a base case and a recursive case. In this method, we have 2 recursive cases. But have a base case. Write your recursive case or cases in this example with the assumption that the recursive call will return the correct answer. So in this case, if I'm writing the add method, if my first of all, my base case should be a trivial input-output behavior. So if b equals 0, if I'm adding 2 values and one of them 0, I'm just going to return the other one because a plus 0 is just going to be a, so just return it. And then your recursive case, write your recursive case with the assumption that your method is correct. So I'm just going to assume that the method is correct. If you follow the 3 ingredients, that assumption will be true via recursive magic. So I'm going to return add of a plus 1 and b minus 1. So a plus b should be the same as a plus 1, b minus 1. Because the plus 1 and the minus 1 will equal out. It's going to be the same thing. And the third ingredient here, I got to make sure my hands are on the screen. My third ingredient is make sure every single recursive call you make gets you closer to the base case. And usually, mostly just a tip, tips and tricks here, is try to get just one step closer to the base case. Don't try to do too much in your recursive step. Just get a little bit closer to the base case. So I have integers here, and my base case is b equals 0. So I'm going to get b just 1 int closer to the base case. If I'm positive, I'm going to subtract 1. If I'm negative, I'm going to add 1. That's going to get b closer to this base case of 0. And I'm going to assume that add does the right thing. So I'm going to assume that it's correct. So I can do this a plus 1 plus b minus 1 will be the same as a plus b. And I can just return that result. And then if I have those three ingredients, everything should just work. And the reason it works is because the assumption is true in the base case. I'm just assuming that the method's right. I didn't even finish writing the method yet, and I'm just assuming it's right. It seems pretty conceited. But it's going to be true in the base case because it's trivially true. B equals 0, A plus B, A plus 0. It's just going to be A, return A. So it's true here. And then in my stack frame right before the base case, it's really relying on add returning the right thing. But that call of add that it made, that recursive call, was the base case, and it's trivially returning the right thing. And then the assumption up here is a little trickier. This method, this stack frame, just assumed that add worked, but it made a recursive call that makes another recursive call. But what that second recursive call got was the base case, and then the assumption kicked in. Now the assumption's doing work for us. If I got the base case as a result, I'm going to do a little bit of logic. +1, -1, that cancels out. And then return. My assumption is going to be true because it's the base case. And now the assumption of the method that called that stack frame is going to be true because +1, -1 cancels out. So now this stack frame's assumption was true because of the logic of this one. This one's assumption was true because it was calling the base case. And this one, it just keeps going as many steps as we need. This one's true because the logic kicked in, and then we get the right return value all the way up the recursion. Yes. Oh, I removed those slides. I'll just talk about that. So if I didn't have a base case, or if I never reached the base case, I'll keep adding frames to the stack until I get a stack overflow error. I'm going to run out of stack space. I'm going to run out of that chunk of RAM that the operating system gave me, and the program blows up. The JVM, the operating system, they're going to step in and say, hey, you're way out of control. Let's shut this thing down because you can't be taking this much stack space. I didn't give you permission to use that stack space. Or it could run infinitely. It can run infinitely if you have something called tail recursion, but I only got a few minutes. Let's talk about some interpretation versus compilation. In tail recursion, the stack frames are reused. This is an example of tail recursion, where the last thing the recursive method does is the recursive call. So these stack frames can actually be reused depending on the compiler and everything. I forget how to do that in Java. Java might just do it automatically. So this one might go infinite, but if you don't have tail recursion, it's gonna blow up with a stack overflow. All right, quickly, this doesn't fit really anywhere else, so I want to jam it in right here. Interpretation versus compilation. I mentioned it a little bit last time, but let's give a little bit more explanation on it. Interpretation is when your code is ran and executed one statement at a time, just line by line, your code is executed. JavaScript and Python were interpreted languages. Compilation is where your entire program is translated into another language first, and then that other language is interpreted. This is what Java is. Java is compiled into Java bytecode, which is its own language, and then the JVM runs Java bytecode. It interprets the Java bytecode. With interpreted languages like JavaScript and Python, you're going to see runtime errors. You're going to see, if you have errors, they're more likely to be runtime errors because because your code is just ran line by line, and then once it comes across something that it can't do, then the program blows up. With compiled languages, you're going to see, if you have errors at all, you're going to see more compiler errors. You're going to see this a lot. IntelliJ is going to find them for you and give you red underlines under the compilation errors. And then you can go and fix those errors before you even run your program. So the compiler is going to check all of your syntax, check all of your types also, since it's Java. And if it finds any issues, it's going to say, hey, you should fix this before you run your program because I can't run this because I can't compile it. I don't know how to translate this into the other language. So with compiled languages, the compiler is looking at your entire program to compile it first. So if there's an issue anywhere in your program, it's going to find that and then let you know, hey, fix this before I can run your code. So your code won't even run if there's an issue. Even if there's an issue in a file that you're not even working on, that's not even going to be used in the program that you're currently running, there'll still be a compiler error and it won't run your language. It won't run your program. In Java, once it's compiled into Java bytecode, it runs on the JVM. If you've ever seen these updates, that's the JVM. Update your Java. Your Java's out of date. That's the JVM. It's installed literally billions of devices, as they like to brag about, which makes Java code very portable. You can run Java on any Java programs, compile them, and run them on any machine that has Java installed. Oh, that's all I got for that. And we're about out of time anyway. Good timing. I guess I'll wait for my alarm to go off. If anybody has any questions. Gerline, you made the post? Thanks. I'm going to say Gerline gets to decide. Do I get to vote? Do I get a vote? All right, so programming test 1 is the big thing right now that you all should be working on. And there's my alarm. What? I don't know how to answer that. All right. So lecture officially over. That's the end of lecture. I'll wait a second to know what meant. Gerline made a poll on Piazza, if that's what you're asking about, whether we should get a 10-minute break in the middle or not. And it looks like the vote's going so far the way that I expected. Unless Gerline decides to have a break. Whenever I've done these polls in the past, it's always been no break. Nice song. I'm gonna get DCMA'd though. As soon as I think I should change my alarms to just beeping, just in case. It'd be an embarrassing issue if a video got pulled down or anything. But I think they mostly just demonetize and then silence that part of the video these days. I don't think they pull down whole videos anymore. When would interpreted languages be better than compiler? Oh, that is a good question. I don't know, never. Let me think about that one for a sec. Because usually the question's in the reverse order. Well, I guess I'll just give the question that people usually give is, so the downside of compiling is that it takes a while to compile. When you're running your Java code, if I want to run some code here, I got this progress bar. That's the compiler. It went pretty quick because this was already compiled. I didn't change any code. But that takes a while the first time that you compile your code. So that would be one of the downsides that would make interpreted languages better. Interpreted languages start immediately. If you start a Python program, I'm not going to have Python. Oh, I do have Python in here. If I run a Python, I don't have an interpreter. Oh, I'm not going to mess with it. But you've ran Python before. If you took 115 here. When you run a Python program, it just runs immediately. So that would be one advantage to interpreted languages, is they get off the ground quick. But that's about where the advantages end. I don't know. I never really thought about that, like why I would want an interpreted language. I usually want a compiled language. Yeah, the whole 116 channel gets nuked because of my alarm. That would suck. I usually want a compiled language because it does a lot more checks. Compilers also do some optimizations for you. As they're translating into another language, they're going to find a lot of things where the compiler looks at your code and says, why the hell would you do it like that? Like, here, let me fix this for you. Let me do it this way. It's going to be a lot faster. So compiled languages are often very, very much faster once they do get running, after they're compiled, than interpreted languages. So usually you want to prefer an interpreted language. I guess why I would want an interpreted language, just because I want to use Python, because Python has such nice syntax that's one reason I use interpreted languages, because Python's so nice. But once you have a larger program and a lot of complex stuff happening, Python usually breaks down. Um, since you don't have the compiler looks for errors and finds a lot of errors for you, and you just don't have that if you're coding a large program in like Python or JavaScript. I have a large JavaScript project right now, and it's just an absolute nightmare. Everything's so hard to find bugs. All right, I'm gonna sign off. I'll take a quick break. I'll be in office hours shortly. If anybody has questions, I'll be there. I would say I prefer compilers. I'm sure you're gonna find somebody out there who says no, interpreted languages are the way to go. But if you're asking me, yeah, compilers. I prefer compilers. But yeah, I'm struggling to even think of like what somebody's argument would be. Why is my computer telling me what the S&P 500 is? I never told you to do this. I'll do that some other time. I'm having trouble to think of what their arguments even would be, though, for pro interpretation. I don't know. The startup time is the only real thing I can think of. All right, I'll be in office hours. I'll head over there in a little bit. See you later. See you Tuesday.